So welcome back, everybody. I hope you've had a good lunch. So my name is Catherine Powell. I'm sort of leading the Manchester contribution to this AI hub. So I'll be chairing the next session. So we've got 4 great speakers lined up. So we've got 4 speakers. So speakers sort of aim for 20-ish minutes, and then hopefully we'll have time for some questions as well. So our first speaker is Hannah Christensen. She's an associate professor in physical climate in the Department of Physics at Oxford, where she leads the atmospheric processes group. Her research focuses on aspects of numerical modeling and uncertainty quantification, which includes the use of machine learning and AI tools for weather and climate prediction. And I believe she's going to tell us about some of these things today. Take it away.
Right. So good afternoon, everyone. It's a real pleasure to be here with you all. And thanks for the great talks and discussions we've already had this morning. So as you can see, my talk today is entitled Machine Learning for Uncertainty Quantification in Earth System Modeling. So I'm very much an applications person when it comes to machine learning tools. And so I'm going to start off by giving quite a lengthy introduction to this area. So really trying to highlight for you how we currently do system modeling, system prediction, and the kind of uncertainties involved so that you can see the ways that machine learning could be useful in this area. And then I'll finish off by giving a couple of case studies towards the end. Okay, so the problem that I'm interested in is predicting how this beautifully complex and intricate Earth system is going to evolve. And I'm interested in this on a huge range of timescales, both the weather forecasting problem, predicting the evolution over a few days, all the way through seasonal forecast, decadal to many decades and even centuries. And the conventional way we do this is that we build computer simulators of the Earth system. So here I'm showing you a schematic of how we might represent the atmosphere and the ocean in such a simulator. And the key idea is that we know many of the equations of physics which describe the evolution of the atmosphere and the ocean. So kind of central to this understanding of the Navier-Stokes equations, which describe how a fluid moves, how the air and the ocean move on a sphere. And what we do is we encode these equations, we discretize these equations, put them into our simulator, and we step them forward in time to predict the key variables of state. And those are temperature, our horizontal winds, and our humidity. And so we predict a value for these variables at every single grid point over the globe, going up into height in the atmosphere as a function of time. But the problem is that solving just these Navier-Stokes equations is not sufficient. And that's because of this thing I've already mentioned, that we've had to discretize them. And the discretization scale that we might use in a weather forecast is of the order of a few kilometers. And in a climate model, it could be more like 50 to 100 kilometers. So there's a lot of stuff going on at scales smaller than that, which we're not explicitly calculating in our model, but which are important for how the air and the oceans evolve in time. And so we have to capture these effects in our model in some way. And we do this by building what are called parameterization schemes. So these are simplifications of various processes which happen at these smaller scales. So if we take the bottom left here, which is showing some of the parameterizations in the atmosphere, we can see that we're representing things like radiation, clouds, convective thunderstorms. And there's one aspect of this schematic I'd like to highlight, actually. So I've shown this parameterization scheme as coming out of a little column in the atmosphere. And this is actually what we do. So our parameterizations tend to be localized in terms of space, in terms of horizontal space, but can see all of the variables in the column. And this enables us to capture things like, how radiation propagates through the atmosphere, how a thunderstorm develops in the vertical. But in general, we don't know information about the neighboring columns. So this will be important later. Okay, so having built our simulator, how do we then make a prediction? So we can use our simulator for both weather and climate prediction, but it's subtly different how we use it. So for weather prediction, the first thing we need to do is to work out what the state of the climate system is today. And so we have various observational measurements from satellites, weather balloons, and so on. We blend these together with our model to give us an initial state which spans the whole globe, every one of these grid points. We then we plug this into our model, and we step our model forward in time to produce our weather forecast. And so what we end up with then is a snapshot of the weather conditions at a given point in time. And you can take this then for a particular location. This is what you get if you look at the Met Office app or something on your phone. The climate prediction problem is subtly different. So we're not so concerned about the starting conditions, the kind of precise starting conditions of our model. Actually, the thing that we're more concerned with, that is more uncertain, is that we need to estimate how our greenhouse gases, how our anthropogenic forcings are going to change into the future. So we start off by running some socioeconomic models, which help us come up with a possible plausible pathway of how these emissions are going to evolve. And then we combine these with a very similar model to what we use in weather forecasting, except that this model tends to be run at a lower resolution, so it has bigger pixels, so it has to be run for longer. And it also has extra kind of complexity added on, so things that are important on climate timescales, but not important if you want to predict the weather over the next week. So these are things like ice sheet dynamics, the biosphere, and a carbon cycle. And then the thing that we are interested in at the end of the day is also subtly different. So while we do actually step this model forward in the same way as a weather forecast model, what we want to get out of it at the end are the change in the statistics of the weather. So we might look at, say, the frequency of a heat wave over a 20-year period centered on today and compare it to how this frequency of a heat wave looks for a particular location centered on 2100. But we're more interested in this change in statistics. Okay, so there are various key uncertainties associated with these two prediction processes. So firstly, in weather forecasting, there's a key uncertainty which comes from our lack of precise knowledge of the initial conditions of what the weather looks like today. And the reason that this is a problem is because of chaos. So the atmosphere is chaotic. We can have tiny errors in these starting conditions which exponentially amplify in time and move from the tiniest scales of order a few kilometers up to changing the location of a weather front over a few days. And so this is something which causes a lot of uncertainty in the forecast. The second big source of uncertainty is that we're actually making a prediction using a computer model. Like I've said, we've had to come up with various approximations in building this model. And each of these approximations, while again they might be localized in terms of the source of error, these errors kind of cascade up to larger amplitudes but also larger scales. So for example, we might mispredict how strong a convective thunderstorm should be, but this can interact with the rest of the atmosphere and ends up to some macroscopic mispositioning of a weather front or so on. This is a large source of uncertainty in weather forecasts. On the climate projection end of things, we're not so concerned with the initial condition uncertainty to first order, but model uncertainty is still a problem. So here, model uncertainty manifests as the model details in how we represent small-scale processes in the model can actually change how readily that model warms when we put in, say, carbon dioxide or other anthropogenic forcings. So these details in how we represent clouds, for example, we know are very important here. And then finally, we've got forcing uncertainty. So we said we had to come up with this emissions pathway. This is something which, of course, we can't possibly hope to know, but we just have to come up with something that's plausible. So because model uncertainty is common across weather and climate prediction, I think this is a really interesting area to work in. But it's also going to be then the focus of my talk. So how can we use machine learning to kind of address this issue of model uncertainty? Before I go any further, I wanted to mention one final thing, which is how we practically represent uncertainties in weather and climate prediction using our conventional models. And we always do it using an ensemble approach. So what we do is we take our model or models and we run many predictions for the future. We view each of these predictions as being equally likely in some way. And the aim of this process then is to ensure that the different predictions are somehow capturing these different sources of uncertainty in them. So, for example, if this was a weather forecast, we would make sure to try and quantify our uncertainties in the starting conditions and make small changes between the different predictions. And then you run the models out into the future and see how they then diverge after 5 or 10 days. If we're thinking about forcing uncertainty, we can try different runs with different possible emissions of greenhouse gases. But model uncertainty is actually a really tricky one to work out how to represent. But we have to do it for both weather and climate prediction to ensure that our forecasts actually diverge enough from each other and span what will really happen. Okay, so I finally got on then to machine learning for Earth system modeling. And so the goal here is twofold. So we can either think of machine learning as being a really useful tool that will help us speed up our models. And this is really useful because if we can speed up our models, we free up computational power that can be used for something else. So for example, we can reduce the pixel size, increase the resolution of our model, and explicitly calculate the evolution of some of these small-scale processes. The complementary goal, one which is not so relying on a speed-up, is that we can actually use machine learning to improve our models. So I've already highlighted that we've got these approximations that we use, these parameterization schemes, to represent subgrid unresolved processes. And these parameterization schemes involve many approximations. They've been built by many people over decades. And there's a real space where we can improve these by bringing in the latest observational or very high-quality model data. And so since we know that parameterizations are the largest source of uncertainty in our models, this seems like a really natural starting point for machine learning to try and improve the situation. So the idea is that we can swap out one or more parameterization schemes or bits of parameterization schemes with something that we've learned from data. One of the benefits of this is that we keep those laws of physics that are encoded in the dynamical core, so the Navier-Stokes fluid dynamics equations. But at the same time, we have potential to really speed up this situation. As a kind of rule of thumb, you can think that it takes about 50% of the compute time to do the dynamical core, but 50% to do these approximate parameterization schemes. So there's a lot of room here to speed up our model. And I've got here a really simple kind of neural network schematic. And I wanted to talk about this so you have a clear picture in your mind of what we're doing. So what we're doing is we're inputting, our features that we're inputting then are the variables of state of the model. So this is temperature, winds, humidity, going from the surface up into the air, generally localized in horizontal space to kind of fit in with the framework with which we've built this model. We can also put in other fields as we like, maybe telling it whether we're over land or over sea, surface pressure, and so on. But the goal is then to predict the change in these variables over one time step that's due to these unresolved processes. So this is because we're getting the change due to, say, the large-scale fluid dynamics. This is advection of temperature and so on. We're getting that already from the dynamical core. So we just need the bit that comes from the unresolved processes. Okay. And there are various challenges associated with this goal that we've set ourselves. So the first challenge we can talk about is physical constraints. So we clearly need we need a good state dependency in the prediction that we make. We need to obey physical laws like conservation of energy, conservation of water, and so on. Ideally, we would also like to be able to extrapolate. So we would like our neural network or our other machine learned model to work well in a future climate, even though we've trained it using data from today's climate. We have technical challenges to do with data sources, to do with how we couple a machine learning and a dynamical model together. And finally, we have uncertainty quantification challenges. So what we really need to do is to learn this distribution of the unresolved tendency. And then we also need to learn how to draw from the distribution. Particularly, we know that it's important to have spatiotemporal correlations in terms of the draw. So what I'm saying here is that errors coming from the small-scale processes are not white in space and time. They should be correlated between neighboring grid boxes. And so I'm now going to give a couple of case studies of where we've had some successes with machine learning, and I'm going to focus on the uncertainty quantification challenges. So firstly, a really simple starter case study of how we can use a machine learning approach to learn this distribution of some unresolved process. So this is work done by Greta Miller at Oxford. And so the challenge that we've identified is that our models actually really struggle to predict where and when convective thunderstorms should happen. And this is a really important problem because in the structure of the model code, the convection bit, the convection parameterization scheme, is not called as a default. So what we do is we step through these other processes, radiation, turbulence, and then we come to a fork where the model has to decide whether it thinks there's going to be a thunderstorm or not. And this triggering of the convection scheme is something which is a source of a whole bunch of issues in a lot of our predictions. And one of the reasons it struggles, actually, is that many of the conventional predictors we have are deterministic. But we know that this is clearly not a deterministic problem. There isn't a one-to-one mapping between the information we know on the 10 or 50-kilometer scale and whether there are thunderstorms happening at the smaller scales. So the solution that we tested a few things, but we found that a random forest model is a good approach to predict the likelihood of having one of these convective storms at a particular point in space and time. So we've trained this using some high-quality observational data from a particular observing site. And I'll just say that we've put in a bunch of different input fields, which are known/believed to be important for predicting convection. And the reason this believed is an interesting point is because what you can do, having trained one of these models, is actually go back and then interpret where your model is getting skill and use this as a way to improve our understanding of the physics of these kind of processes. I should say it's a fairly unbalanced data set, so we had to do a bit of rebalancing as well. What we find is that the random forest does a really good job at producing reliable predictions. So what I mean by this is that it provides a probability of convection. If we collect together all the days and all the times when the random forest gave a particular probability and look how often convection did occur in that bin, we find that there's a really good match between the predicted and the observed probabilities. And moreover, it has pretty good resolution. So it's able to produce predictions which span this probability space. So it's not always predicting the climatological likelihood of convection, which is admittedly a reliable but not very useful forecast. We think that maybe some of the good performance here comes from the fact that we're averaging over many decision trees just in the architecture of the random forest. So we're somehow accounting for uncertainty in this classification process. Coming back to our considerations here. So we've shown that fairly simple machine learning algorithms can give us good ways of learning distributions associated with weather and climate data. But how do we draw from these distributions? We've broken this spatio-temporal correlation problem up into two. And so I'll just talk here about temporal correlations. And here we found quite some success with using recurrent neural networks to generate draws from this distribution. So RNNs, maybe it's not surprising because they're designed to reproduce a time series. They're trained they're trained in such a way they have this hidden state, which they track in time. You don't have to specify what the hidden state is. The RNN learns the hidden state. But in doing so, it allows to create these long temporal correlations in what it generates. So this is work by Ragul Parthipan, who's in Cambridge. And he tested this approach on a simple kind of atmospheric toy model. In this model, X is the variable of state, and U is what we call the tendency, the change in this over a time step. He broke the problem up into two. So he had a kind of a fairly simple neural network which predicted the most likely tendency. And then he used an RNN to predict the parameters of a distribution, which would give us the kind of stochastic correction to this mean tendency. And in this way, he was able to get a really good temporal characteristics for this draw. I'd go through this quite quickly. So what he found is that the RNN in blue outperformed two other models we tested. So one which was a fairly kind of handcrafted model, the red one, and one which was a generative model, a GAN. What we want to see in the weather forecast plot on the left is that the dashed line, the spread, matches the solid line, the error, in a statistical sense, because this means that your ensemble forecast has spread out enough in time. And what we find is that the RNN does the best job here. It's quite interesting it does better than the GAN, but I think this is because the GAN that we tested had a fairly simple correlation structure in time, whereas the RNN had this much more sophisticated approach. We also do better in the kind of climate simulation problem in simulating the statistics of the system. So to summarize, machine learning for model parameterizations it's an interesting way of approaching the problem because we keep some of the core physics, which is, say, the physics of the fluid dynamical equations in this dynamical core. And we can solve these with quite high accuracy, so we have no need to throw them away. We can learn something about the physical processes, but there are challenges involved with this approach, conservation, stability, extrapolation. But it's worth saying that we have experienced many of these challenges before. So these are not alien challenges. These are things which conventional parameterization developers have also experienced. So if I can have 2 more minutes. There is obviously another way that we can go forward with this problem, and that is to throw away the entire model. And so instead of keeping the dynamical core, we can use observational data sets. So we have 40 years of high-quality observational data. And we can train a machine learning model to just leap us forward in time, either leap forward 6 hours and roll it out, or leap forward some window that we choose. And there are still challenges here, but we've got rid of the challenge of having to combine a machine learning model with a dynamical core, which is actually quite a tricky thing. And so what I'm showing you here is one forecast for now, initialized on Sunday, produced using a state-of-the-art deterministic dynamical model, and 3 that are made with different, very exciting machine-learned models. And I would argue that you would have absolutely no way of telling which one is the dynamical model and which one are the machine learning models. I can take guesses, but it's this one at the bottom right is the dynamical model. And these other 3 are 3 models that have come out in the last year or 2, which have really kind of rocked the community in terms of their performance. ForecastNet, GraphCast, and Pangu Weather. These are all deterministic models, but there has been some preliminary steps in moving towards uncertainty quantification for these pure machine learning models. So in particular, GenCast came out on the archive around Christmas from Google, DeepMind. And this is using a generative diffusion model combined with a graph neural network to make probabilistic forecasts. And what I can say is that the lower the better in these metrics. The GenCast, the blue line, is outperforming the benchmark dynamical ensemble forecast from ECMWF, from a leading weather forecasting center. And so this is very promising for weather timescales, but there's a lot of work needed before it could be useful for climate. This model is unstable if you roll it out for more than, say, a few tens of days. But nevertheless, very exciting. So this does bring me to my final slide. I've talked about a lot of these things. Maybe I can highlight this point on uncertainty quantification for system modeling brings about some quite unique challenges, particularly to do with kind of correlations and how we can deal with uncertainty estimates here. And so I'm very open to hearing suggestions from this community of experts in probabilistic AI. And these pure data-driven models are really exciting, but they need some more work before they can be used across this whole timescale. So thank you very much for listening.
Thank you very much for the excellent timekeeping. I think we've got time for one or two quick questions. Anyone wants to ask? One here and then one there.
Very interesting, thank you. You mentioned that it is also interesting to find the factors that count in your effects, right? And this is connected to explainable AI. It's not easy. So can you say a little bit more about that part?
Yeah, of course. I don't think I have a relevant slide to bring up. But so, for example, for the case of the random forest, you can look at feature importance, or we computed the kind of Shapley values. And then by doing so, you can see where the random forest is looking when it makes its prediction. So quite an interesting approach that my student was using is to do a kind of clustering analysis in the space of the Shapley parameters. And this allows you to collect together the days which the ML model has identified as being similar. And this, by doing this, it actually naturally separated the data into days when it was certain there was convection and certain there was no convection, and days in the middle where it was uncertain. And so then by looking at which features are coming out at the top of those, you can actually learn something about the predictability of convection and see which of these kind of conventional triggers that we use are basically completely unimportant when compared to other variables. Thanks.
The second question.
Thank you very much for your talk. You mentioned, for example, replacing completely the computational model with neural networks, and that means that we're using through backpropagations, we have derivatives, and we can then solve Navier-Stokes. But do you think, so for example, what would you constrain the model on? So many people were showing, oh, if I use the residual of my PDE, that can help during the optimization. But when you look at the papers, usually that contribution is very small coming from that. And things that work is, for example, divergence-free condition and just constraining on that. Is there something else that you would suggest here?
Yeah, so I think this this idea of bringing some of the physical constraints into these pure data-driven weather forecasts is really exciting, but is not something that has been done. So these different models, which or these kind of different predictions that I showed a few slides back, wherever they are. So these models, the cost function is basically the mismatch between what it's predicting at 6 hours and what was observed 6 hours later, or indeed for longer horizons. And one of the problems that you then get with some of these models is you roll them out into the future. The effective way they do uncertainty quantification is they blur the fields. So you start seeing the fields get smoother and smoother as you go out to longer horizons before they kind of blow up in some way. But I think that this area of then like bringing in the PDEs and as a way of trying to still make use of our knowledge about the Navier-Stokes equations and fluid dynamics equations is something we've seen in more simple kind of dynamical system tests, but I mean, is probably somebody, a big industrial partner is working on it as we speak. It will come out in the next week. Thanks.
Okay, I think there are lots more questions, but in the interest of time, I'm going to ask if anybody has any more questions for Hannah to please catch her over coffee, and let's thank her again.